Hello, Coach Travis here with another calculus video. So what we've got here is we've got an antiderivative initial value problem. So the idea here is they're telling us a derivative. They're giving us the derivative of y is this function here. And they're telling us a little bit about y. They're telling us that when you put -8 into the y function, you get 4 out. And what they're asking us to do is they're asking us to find the value of y. So we're told a derivative, and we're trying to find the original function. And so that means it's an antiderivative problem. And what makes it an initial value problem is the fact that they give us this little bit of extra information about the function. They tell us that when you put -8 into the function, you get 4 out. So in general, finding antiderivatives, you can't find a unique antiderivative. But if you have an initial value, then it turns out you can. So we'll see that as we do this problem. So first things first. So let's think about what an antiderivative is going to look like. So we know that dy dx is equal to -4e to the x plus 8. The problem told us that, so I just like to rewrite it to get my mind into the space. All right, so finding antiderivatives is kind of a tricky thing to do, and guessing and checking is one of the best tools we have to find antiderivatives. So why don't I just make some guesses over here in red, and then we'll check them and see what happens. I know that when I find the derivative of e to the something, that the derivative doesn't change very much. So I might guess I might guess that my function is e to the x plus 8. And now let's check. So how do you check? You check by finding the derivative. So I get dy dx is equal to, and then let's see, I'll use the chain rule here. So the derivative of e to the x plus 8 is e to the x plus 8, and then I have to multiply by the derivative of the inside, but fortunately the derivative of the inside is 1, so that's no big deal. So I'll just erase it even. But if you look at, I didn't quite get what I wanted, because I was supposed to get a -4 out here. But I didn't get a -4. Oh, okay, well that's super easy to fix, because what if I just put a -4 here? If I put a -4 here, well, that's a constant multiple, so the constant multiple rule says that when I find the derivative, it's still going to be there. So this is sort of an example of the art of guessing and checking. So when you're guessing and checking, don't worry about getting the correct answer on your first guess. Just guess something and try it. And if it works, good for you. You got a lucky guess. But if it doesn't work, then think about what you could change to get closer, and then make another guess. And maybe that guess is right, or maybe it's wrong. But if it's wrong, probably it's closer, and you can think about how to modify it. So guessing and checking, if you're not used to guessing and checking, you should start practicing it, because guessing and checking really is one of the best tools we have for finding antiderivatives. Okay, so where did we go with this? Okay, so what did we learn from this? What we learned here is that, that y should be equal to -4e to the x plus 8. Okay, but not so fast. Remember that whenever we find antiderivatives, we always have to add the plus c. So what we've got right here is this is the most general antiderivative. So what this function does is let me highlight it. This function right here satisfies this part right there. But we still have this big question mark about the C. And that's where we're going to use the second part of the second part of the information that the problem gives us. So all right, well, so let's see how that works. So what I do here is I say, okay, well, the information they give me says that when I put 8 in for x. So this is really weird notation. This is just what this is saying. Well, it's not that weird, but it's kind of non-traditional. I'm thinking about y as a function and x is the input, right? I mean, you can see it down here. Y is the output and x is the input. And so this is just sort of fancy language for saying that x is equal to -8. So if I put -8 in for x, the problem tells me that I get 4. So I have to get 4. Okay, but wait, not so fast, because I know something about the y function. I've got the y function over here. So I can say, all right, the y function, it's -4 times e to the x plus 8. But wait a minute. Actually, I should have used colors before. Let me change that to make that a blue. So I'm color coding the -8 is the input, and it's going to be in blue. And so wherever I see an x in here, I'm going to replace it by a -8. And then plus c. Okay, so what happened there? What happened there was just everywhere I took my function, my function for y, and everywhere I saw an x, I replaced it by a -8 because that's what the instructions were to do. They said, okay, when you put in x is equal to -8, then you get out 4. Okay, so then now let's simplify this. -4, this is -4 times e to the 0 plus c. Oh, but e to the 0 is 1. So that's -4 plus c. And all of this is equal to 4. I never changed, the left-hand side never changed. And so now you can solve for c. So if I add 4 to both sides, I have c is equal to 8. And so now we can get rid of that c. We can say that y is equal to -4 times e to the x plus 8 and then plus 8, because we've decided that the c had to be 8. And that would be my final answer. So again, the process there is that when you're just given a derivative, you can only find your antiderivative up to a constant. But if you're given a little bit of extra information about your function, like in particular if you're given 1 point on the graph of your function, then what that allows you to do is solve for that c, and then you can get a very exact, you can get a single exact function.